So if we can move to the first slide after the title. Okay, so just to give a broader global context, this shows some results from the IPCC special report on 1.5 degree Celsius pathways, which was released in 2018, and they analyzed 85 different scenarios that achieve 1.5 degrees Celsius by the end of the century. And broadly speaking, I've highlighted below a scenario that looks at the electricity generation by fuel across certain benchmark scenarios. And what this entails basically is that across all the dozens of scenarios that the IPCC analyzed, at least for this report, nuclear energy roughly doubled by the end of the century in most of them, but the share of global electricity remains relatively small, under 10%. And the reason is that solar and wind far outpace all other sources. Solar and wind are shown next to the highlighted region that I have there in light blue and yellow. And it remains to be seen whether this is realistic or not. But the overall point is that nuclear energy does significantly increase in terms of raw output, and the global energy mix overall does become much more electrified. So in other words, electricity is a much higher share, roughly triple of the global energy mix than it is today. If we can have the next slide, please. Okay, so just to zoom in on the U.S., this shows CO2 emissions for the latest data that we have, anyway, by fuel for the last century, and since 1900 basically to 2018, and you can see that the U.S. emissions have declined. Again, this is fossil fuel CO2 emissions only. They have declined over the past 10 years or so. And that's the red line at the top. And if you look at the black curve, that shows coal specifically, CO2 emissions from coal. And you can see that the overall emissions are declining largely because of the decline in coal. And that in turn is happening mainly because of the fuel switching that's happening in the power sector from coal to gas. So in a sense, that's a very good thing in terms of both CO2 emissions and fatal particulate emissions. But U.S. CO2 emissions are still number 2 in the world by a long shot. So, and the bottom line is, just one sec. So fossil fuels still account in terms of the overall U.S. energy mix for over 80% of national energy and over almost 2/3 of our national electricity, whereas the non-hydro renewables, solar, wind, and biomass, only account for about 5% of national energy and 10% of electricity. So next slide, please. Okay, just one thing. Sorry, is my video distorted by any chance? Or can you see me okay?
Yep, looks just fine.
Okay, great.
You bet.
Okay, great. Okay, so zooming further into New York State level electricity generation CO2 emissions. These are graphs I just made yesterday, actually, in preparation for this talk. And obviously, we won't go through every detail, but they show on the top, the top row shows a statewide electricity generation in New York, on the upper left by fuel source, so all the different fuels that contribute, and on the upper right it's aggregated source percentages. So in other words, like the percent of total statewide electricity from fossil fuels is the red curve, followed by nuclear, the orange curve, and then hydro is the blue curve. A dashed curve is actually Indian Point reactor number 2, and then the other 2 curves are biomass and solar and wind in green. And you can see just from these curves that roughly, and the stats I've highlighted there in the text, gas, like natural gas, provides roughly 38% of the state's electricity right now, and the rest of the fossil fuels are coming from a minor contribution from oil and coal. And about 1/3 of the state's electricity is coming from nuclear, whereas about just under 1/3 is coming from renewables, but the vast majority of that is from hydro. So solar and wind, at least as of these data, they end in 2018. I like to look at annual data, so these are the latest data that I've seen. they show that the solar and wind together account for only about 3% of New York's electricity. So that's important to bear in mind that Indian Point Reactor 2 alone accounts for about 6% of New York statewide electricity. So if we had any hope of replacing that with non-hydro renewables, they basically have to double their share overnight, which is virtually impossible, obviously. So it's almost certain, and I'm sure some of your previous speakers have addressed this. Unfortunately, I was unable to join until now, but it's almost certain that it will be replaced by gas. And that has implications for CO2 emissions from the electricity sector of New York State, which are shown on the bottom left. So we can get to that curve now, and you can see again it's divided up by fuel. And the total fossil fuel emissions from electricity are shown in the red curve. The purple curve is gas. The black and brown curves are coal and oil. And you can see that basically coal has virtually dropped to zero. And so in that sense, New York's done an excellent job on a statewide basis anyway of reducing coal, dramatically reducing coal. And again, as with the U.S., the main cause of that is the fuel switching from coal to natural gas. Of course, I'm sure your other speakers have addressed this too. Most of that gas is coming from the shale revolution, so fracked gas from my home state of PA, actually. So in any case, you can see if you look at the red and purple curves, in other words, the total fossil and the gas curve, you can see that over the last 10 years or so, fossil fuel emissions are essentially driven entirely by gas used in electricity in New York State. So see there's a slight uptick over the last year of data that we have. And if Indian Point is indeed replaced entirely by gas, which seems likely, as I said, you'll see a further uptick of about 30% of total state. So that red curve will go up to about 38 megatons, so million tons of CO2 per year. And that will obviously hinder New York's climate efforts and air pollution mitigation efforts. Although, thankfully, gas isn't as bad as coal, the real problem here are the CO2 emissions. The next slide, please. Okay, so on a broader basis, globally speaking, why is nuclear important? Many of you might be familiar with my and Jim Hanson's paper that we published in 2013. We looked at simple counterfactual scenarios, asking the question, what if nuclear power never existed globally? And the upshot of this work is that over the past 50 years, so since the early 70s, the spread of nuclear power globally has helped to prevent over 2 million deaths that would have been caused by fossil fuel burning in the electricity sector, air pollution-related deaths. And so this is thousands of times more than it has caused in its entire 60-plus year history, nuclear energy. So, and the projections show that through mid-century, nuclear power could prevent up to an additional 7 million deaths. Again, these are air pollution-related premature deaths. And prevention of morbidity, so in other words, serious illnesses requiring hospitalization and so on, including illnesses, by the way, that make people much more susceptible to COVID-19 and other respiratory types of pandemics. Prevention of serious illnesses like those was a factor of 10 higher than the mortality numbers shown here. So nuclear power has made a huge contribution in terms of human health historically on a global scale. The next slide, please. And environmentally speaking, the story is similar. We find that, again, if you look at the uppermost bar graph, over the past 50 years or so, again, we analyzed just until 2009, but I've done some offline calculations, and we show that the numbers only increased to just under 80 gigatons CO2 cumulative that nuclear has prevented over the past 50 years or so. And that's equivalent to several hundred large coal-fired power plants never having come online. Or, if you like, the past almost half century of coal burning in the U.S. And again, our projections show that through mid-century, the prevented death, if nuclear displaces fossil fuels, could be in order of magnitude higher, almost several hundred billion tons of CO2 cumulatively. Next slide, please. Okay, so fast forwarding to a paper that we published, I published with my other colleague, Makiko Sato, just last year, a peer-reviewed paper in the journal Energy Policy. Many of you may not be familiar with this one. We examined energy, electricity, and CO2 emission trends since the Fukushima accident in both Japan and Germany. And the reason we chose these two countries was that they were the most strongly affected by the accident for different reasons, as I'll briefly get into. But we asked similar counterfactuals in this paper, which is what if both countries had reduced, instead of reducing nuclear power as they did in a sudden and drastic way after Fukushima, which happened, remember, in about 9 years ago in March 2011. What if instead of reducing nuclear, they reduced fossil fuel power by the same amount? And more broadly, what if the U.S. and the rest of Western Europe, where there are troubling trends, as we know from Indian Point and other places around the U.S., but certainly across most of Western Europe, there are trends, anti-nuclear trends, both in terms of public sentiment and political will to just phase out nuclear, even though in both these regions there have been zero major accidents that have caused lasting damage in any significant way, and even really temporary damage, certainly in terms of human health. Okay, next slide, please. Okay, so in terms of just the energy and electricity findings, what we see are the upper row shows Japan, and the bottom row of graphs shows Germany, and these are on the left column shows electricity generation by source, and the right column shows the aggregated source fraction. And so what we see, if you look at the orange curves in the upper and lower rows, the orange curves show the drastic and sudden reduction in nuclear output. Obviously, it was very severe in Japan, where they shut down essentially all the reactors in a couple of years following Fukushima. And in Germany also, I think we just heard, I did catch a little bit of the last talk, and I think I heard that Germany has now, like just a handful of reactors, I think it's about 6 plants left, 6 reactors left, of the 14 or so that it had pre-Fukushima. And so these represent permanently lost nuclear capacity in Germany. And Germany, as most of you probably know, has plans to, actually right after Fukushima, just literally within weeks after Fukushima, Germany announced, the government of Angela Merkel announced a sudden turnaround where they said, okay, we are going to proceed to nuclear phase out. Otherwise, she came in on a platform advocating nuclear energy reactors, but unfortunately, they reacted, in my opinion, in an irrational way against nuclear. And so they decided right then, and they are on course to completely phase out their entire nationwide nuclear output by 2022. And unfortunately, from a climate perspective, and as we will see from Germany's own climate mitigation goal perspective, they are seeing the impact of that in a negative way. And just real briefly, so the lost nuclear output that we see from the drops in the orange curve was replaced in Japan almost entirely by fossil fuels, whereas in Germany it's a little more nuanced. The situation is interesting. They have been successfully able to replace some of the lost nuclear, actually a significant amount, some of the lost overall electricity output nationally by renewables, but in the first few years it was replaced by coal. Next slide, please. So in terms of the implications for the electricity sector in CO2 emissions in both countries, you can see that there is a bit of good news. Emissions did increase until in the first couple of years after the accident. So in other words, until about 2013, they increased in both countries notably, and that's again due to the fossil fuel power that was used to substitute for the lost nuclear. And those emissions increase did get headlines around the world. including from very pro-nuclear and anti-renewable advocates. But what didn't get as much attention, and this we have to be honest as scientists, and if we're looking into data, it is clear that both countries have done an impressively good job in reducing emissions since then. In other words, the past 7 years or so, both countries' emissions from the electricity sector have significantly decreased, roughly to below pre-Fukushima levels at this point. And the reasons are different in both countries. In Japan, it was because of reduced overall electricity use. So in other words, increased energy efficiency, and in some cases, unfortunately, from what I've read, at least anecdotally, it's resulted in an increase in energy poverty. In other words, like a lack of energy availability in many parts of the country. But in any case, that was the cause in Japan, reduced overall electricity use and energy use. Whereas in Germany, it was due to the remarkable surge of wind and solar that they've had in the past 15 to 20 years, especially. The next slide, please. So that's the good news in terms of CO2 emissions. There was a temporary increase for a few years, then they declined since then. But the not so good news is what I term lost opportunities. In other words, they missed significant opportunities to avoid impact in terms of both human health and the CO2 emissions. And what I mean by that is this is where our counterfactual scenarios come in. If both countries, because this is the key point. This is, if you have one takeaway from my talk, it's this: both countries made the major mistake of reducing nuclear power, which, as most of you know, is a clean energy source from a climate and human health perspective, while they were still continuing the use of fossil fuels for electricity. And in fact, as I just mentioned, they increased fossil fuels for the time being, shortly after the accident. So the upside of that is my analysis showed that in the years after Fukushima, if Japan had reduced fossil fuels instead of by the same amount that they had reduced nuclear, they could have prevented over 23,000 premature air pollution-related deaths and over 2 billion tons of CO2 emissions. And likewise, Germany, which is shown in the black bar in the in the left graph, Germany could have prevented, just in the historical period, in other words, since Fukushima until now, almost 5,000 premature air pollution deaths and several hundred megatons of CO2 emissions. And furthermore, they can still prevent, if they just keep the remaining reactors at their current output and instead focus entirely on reducing coal and gas, they could prevent up to 16,000 additional deaths just if they just keep their current fleet of reactors operational at their current output until the end of their lifetime, which we assumed in our paper to be the middle of next decade. So just another 15 years, if they paused their nuclear phase out and instead focused on reducing coal power, they could have these preventable impacts. And likewise, again, remember our analysis extended to U.S. and rest of Western Europe. Both of those regions could each save over 100,000 lives if nuclear power is allowed to remain at its current output until their fleets also retire, which is, again, we assume to be in the next 15 years or so. And each region could save about 7 billion tons of CO2 emissions by that same time. So next one. Yeah.
Energy usage. Why don't you think governments use statistics like this to make decisions about their energy usage?
Well, one thing, just on a minor note, our study wasn't available, and to my knowledge, no similar study has been done looking at let's say, in the case of Germany, the impact of their phase out. So the implications of reducing nuclear while they're still using fossil fuels. So that's one minor point, which is that studies like this weren't available to them, to the best of my knowledge. But the broader point is that, unfortunately, in these regions, we're seeing like a surge of anti-nuclear sentiment And it's really unfortunate, especially in the broader context that I mentioned, in the global context, if people simply realize that nuclear, if you look at on a historical perspective of it across decades and around the world, the prevented impacts that it has provided are far greater. In other words, the lives that it has saved far outnumber by several orders of magnitude the amount of, even if you look at the upper estimates of the lives lost in the accident. So that's one thing. They just don't keep in mind the broader context, and unfortunately they're guided more by emotional like motivation rather than scientific, objective science. So, but we're trying, we're trying to get our studies out there, our results out there.
Yeah, well, it certainly tells the story.
There's no simple answer to that.
Yeah. Great.
Okay, so just very briefly, I know I'm probably short on time, right? Do we have to go, I guess?
We are a bit over here. If you could wrap it up in the next,
okay, no problem.
That'd be great.
So let's see. This is, I think, we're just about done with the presentation. So anyway, so the upshot of this slide is that both countries, in the case of Japan, this slide shows their CO2 emissions from their overall national energy use, fossil fuel CO2 emissions historically over the last 20 years, and then projected out to 2030, which is when their Paris Agreement commitments will presumably take effect. And we see that Japan, on the left side, Japan is on course. If you look at if you extrapolate just the last few years of their emissions, they're on course to meeting their Paris Agreement target, whereas Germany is going to overshoot it by somewhere around 15%. Again, if you extrapolate the current course. The problem is, if you just looking at the Paris Agreement commitments, it might seem like, okay, that's not so bad. But as many studies, including the UN's own analyses, have shown, the Paris Agreement commitments are woefully inadequate. They will lead to global temperature rise by the end of the century of far greater than what the vast majority of us climate scientists consider to be safe levels.
How much are we talking? 2.5, 3 degrees Celsius more?
More, so 3, possibly even 4 degrees Celsius by the end of the century. Remember, that's if the Paris Agreement commitments are actually achieved. So Germany is not even on course to meeting that, and in a significant way, it was caused by their decision to phase out a clean energy source, a non-fossil energy source, nuclear, while still using fossil fuels to generate about 40% of electricity, which to me is just complete folly. This is the key point again, and if we get to the next slide, it's just about them. I'll just rush through. So yeah, in terms of success stories though, so we've had good and bad news. In terms of success stories, you can read this, like most of you probably know these stats, but so I won't go into the details, but I'll just get to the bottom line, which is we need all available non-fossil energy sources in the global energy mix. Renewables by themselves, or even nuclear by themselves, are simply not enough. Okay, next slide, please. This is the last slide. Okay, so the key takeaways from our studies and many others around the world is that it's just folly. It's totally counterproductive to oppose and even phase out a proven low-carbon source like nuclear, given that every source has its pros and cons. So most of you probably know that there's many challenges to implementing very large-scale renewables like solar and wind, as well as challenges to implementing very large-scale nuclear. But that doesn't mean we should disproportionately focus on the negatives of one energy source over the others, which is unfortunately the case with nuclear. It's gotten like widespread negative if something goes wrong, but people forget the broader global context that I mentioned. So again, there's no universal energy solution. And the energy mix has to be customized to whatever region you're considering. And lastly, I'll reiterate this, like this can't be stressed enough, before or instead of cutting nuclear output or any clean energy output in the near future, countries and states like Europe should really target their fossil fuel use instead.
Yeah.
So thanks.
Thank you. Thank you for joining us. And yeah, that's some heavy stuff. It's so frustrating, right? Because if if we had a celebrity, if we had a Mark Ruffalo or a Leonardo DiCaprio, maybe we could communicate these facts to a broader audience. It's one of the struggles of those of us who consider ourselves, pro-nuclear environmentalists. But I really appreciate your research. I've told countless people about the 2013 study. Now that the 2019 is out, that makes my advocacy easier to do. Being able to point to this and show it's not just about climate change. There's real human health impact here that we need to address in our decision making. I really appreciate it again. I'm checking for any questions. Oh, there's one. What will your next paper be on?
Yes, good question. Well, it's been in the works for a while, unfortunately. A bit slow to crank it out. But in any case, it's going to be on analyzing, I mentioned these 1.5 degree scenarios in the IPCC report. So one part of it will be looking at the implications on a sub-global scale. So backing up a bit, so globally speaking, most of the scenarios that people discuss in terms of achieving 1.5 degree or even 2 degrees or whatever temperature target you want to talk about by the end of the century or other time frame, most of those are analyzed on a global scale. So in other words, the IPCC reports and so on, the National Academy of Sciences, most of those focus on very large scales. But relatively few studies, there are some exceptions, but relatively few studies have looked at what this means in terms of implications for individual large CO2 emitters. So in other words, what does China need to do specifically? What does the U.S. need to do? What do these countries individually need to do in order to meet these targets? And again, that's embedded within these global results. But my next paper, I want to zoom in on these individual countries and really look at the implications of these stringent mitigation targets for the individual CO2 emitters.
That makes a lot of sense in helping drive decisions within those countries. So I'll look forward to that. Maybe it'll be done before the next climate talks in 2021.
Yeah, hopefully. Yeah, that's actually a good goal. Yeah. Right. I'm hoping it'll be submitted, sometime by the end of the summer. But as anyone who knows scientists know, things are always not on schedule. So,
yeah.
So we'll see.
Absolutely. All right. Well, thanks again. Really appreciate it. We are working on pulling the train into the station. So, thank you again. We'll bid farewell. You're certainly welcome to stick around for the last part of this.